Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about rotating detonation engine. So let's dive deep into it. Now, I'm not going to go super deep into the science. This is more of economics and how the heck it fits into the technology. So let's take a look at the idea. So what is the idea? Idea is right now we have things, be it rocket engine, be it jet engine, be it your car engine. All of these puppies are running on whoosh. That's what they're running on. Somebody had the idea, instead of running on whoosh, what if we run on boom? So what does that mean scientifically? Scientifically, it means like we are running on combustion. Whole our society, civilization runs on combustion. Now, key aspect of combustion is that flame front. Basically, if you have a tube and you have things there that could go burn, basically be it oxygen, be it fuel, and you have that mixture, it will take fire. Now it will burn. Now, how quickly that basically flame front moves, that is the key here. So if you have a combustion, all you're gonna get is basically a lot of heat, lot of pressure and high speed gases. That's good, but flame front will never reach supersonic. Now supersonic, again, according to what? Now this is very critical aspect. Supersonic to the local environment, meaning if it's a solid, it has that sort of variation into it. If it's a liquid, it has that variation into it. If it's gas, it has that variation, basically of local material. Basically, if it's you're talking about gases, it has to be supersonic in the gas. If it's a solid, it has to be supersonic in that solid. Everything has a different Mach value, but it has to be supersonic in that medium, quote unquote. So normally every time when you do things, we are talking about combustion, and that's why when rocket goes boom, they are not that powerful when you are talking about, like for example, SpaceX launched Starship upper stage had full fuel, full oxidizer, but it went boom. It was very mild. Now, why the heck it was mild? Well, because it was in combustion. It was not in detonation. Now, whenever you look at this sort of thing, this is a shock wave. You see, like air simply cannot move out of the way and it's being compressed in that zone. We call it shock wave. So detonation is that key aspect. When you are releasing energy so fast that flame front, basically where reaction is happening, it's supersonic in the medium. Now, what does that mean, supersonic? Supersonic simply means the unburnt part, basically the part where you have the reaction, and the part that does not have the reaction, cannot move out. Basically exactly like how sonic booms are formed. Your plane is moving so fast, the air molecules cannot move out of the way. They get compressed, rather than, okay, just move away, move out of the way, it gets compressed. Same thing is happening when you have detonation. So if you have detonation, things cannot move out of the way. So you are pushing so much energy and it's so fast that from here to here, there is no pressure rise here. It's like nothing, and bam. So when you have combustion, it's like pressure like there is a curve to it. Pressure goes up, temperature goes up, it goes down. Shockwave is like nothing, bam. So this is the whole point. And that's why whenever you see a rocket going boom, there is always such a slow, thing going on. When you're talking about like basically boom devices are like, unless you have high speed camera, all you're gonna see is like, after effect of it. There will be a flash and then you see the after effect of it. So why is that? Well, again, when you are talking about rockets, they are going into basically burning. They are combustion product. When you're talking about booms, you are talking about detonation. Now, one thing is very critical in terms of energy, basically how much megajoule you are talking about. It has no direct correlation here, meaning which has more energy, basically 1 liter of petrol or 1 liter of dynamite, basically by volume. You may say dynamite, but no, it's petrol. It's like, wait a minute, what the hell? How the heck RDX has less power than basically petrol? Well, petrol is a two-part component, meaning it requires oxygen to really yield itself. The reason why dynamite is so powerful is simply because it can release all that energy in detonation, meaning the megajoule you have per liter, it's one vector. Now, how quickly you release that defines your energy output, meaning you take all that energy, you dump that puppy in 1 second. That's a powerful fire. You take all that energy, release that in 1 microsecond. That's a lot of energy. That's like oomph. That's what we are talking about when we are talking about booms, and that's what you have to understand when you're talking about energy. Jet fuel has a lot of energy. It's just, it can't release all of it instantaneously. And if somebody figured out how to release all of that instantaneously, it's gonna be a big bad day. So that's the whole point of having shock waves rather than basically flame front. Shock waves. Now, what happens when you are talking about that shock wave? The temperature and pressure, both of these puppies become extreme. Like very, very extreme. And the velocity, it's also becomes stupid. Like what kind of range we are talking about? You are talking about combustion, which has a range of around 1 meter per second. That's fast. Versus shock wave that could have speed of 1 kilometer per second. That's why I said supersonic in the medium. It's very large gap, like very large gap. And that's why I said like the shock waves are so fast that if shock wave is coming to me, I cannot feel it. Like if a combustion is coming, I will feel the pressure rising and then going to the apex. When shockwave is coming, it's like nothing, and bam. So that's the aspect of having 1 kilometer per second kind of velocity. And it's very, very quick, meaning the energy content is the same, but it's released so quickly, the oomph of it is much, much higher. And it's very violent. Violent as in like the turbulence, the chaos is super, super high. Entropy, super high. Energy release is bonkers. So that's the science behind it, as simple as I can make it. It's just, instead of burning things, which is very gentle, very calm, very controlled, we go boom, where you have such a high speed energy release that things cannot even move out of the way. You are creating a shock wave. The temperature is bonkers, the basically pressures are bonkers, and your velocity, that's hyper bonkers. That's why we can, even taking the same jet fuel, if you have a basically detonation happening to it, you can get much faster plane. So that's the idea. That's the idea. So what about the progress? Like the idea sounds old, and it is very old. We had like the earliest paper I could find is 1950, and I'm damn sure there must be some papers that go even before than that. We kind of knew about it because we figured out by the time we were making explosives, we kind of figured it out. Like the reason explosives are not powerful is simply because they can release all the energy instantaneously rather than they have energy. Your fuels like diesels, jet fuel, these puppies have energy, but they cannot release it very quickly. So we kind of knew about this thing. The moment we started to work on dynamites, glycerin, these sort of things, we figured it out. But there is a problem with that. Like we figured it out, we tried to make engines out of it, but problem was the chaos factor was too high, meaning the output, the models that we were trying, like this is how flame front is going to react, none of our model made sense. It was too chaotic. And when early computers came to be, basically 1980s and 1990s, it still could not crack it. 2010s still could not crack it. 2020 still could not crack it. Right now, all you are seeing the research, everybody, every Tom, Dick and Harry who's working on it, they are taking the data, real world data, feeding it into computer simulation to fine tune the computer simulation. We have no idea how exactly this model works. Like we have a guesstimate at this point in time. Is it good enough? Not really, but like we can get something working out of it. And all the prototypes that we have built for decades at this point in time, majority of them simply went boom. We tried to, but it went boom, because again, we are trying to make it boom. And F1 was also very famous for that. You have to understand this way. What is a rocket engine? You are burning something there, and you are burning at very high pressure. It's not just a flamethrower, it's a very high pressure flamethrower. So you have a lot of fuel, lot of oxidizer, and you're burning it. Now here's the deal. How the heck it can go boom in this scenario? When you have this sort of things flowing, how the heck that happened? Because you created a scenario where flame front exceeded Mach speed, meaning instead of flame front being subsonic and getting accelerated through the throat of the nozzle, it itself reached supersonic. The moment that happened, your engine reached a scenario where it had overpressure and it just went boom. So this is the critical aspect. Now, however you design it, like I'm going to have annular structure, basically a donut, and it's going round and round like this, the pressure in that shock wave would be bonkersly high. So every time rocket engines reaches that point where somehow, like let's say a pocket of fuel, pocket of oxidizer reaches a point where it's like too turbulent and did not has the same flow characteristics, there's like a local static pocket, it goes boom. And it reaches a point where we have perfect detonation. The moment you have detonation, your engine goes bye-bye. So all this being said, like even the fact that we work our ass off to make sure that rocket engines do not suffer detonation, the research on this field never stopped. Like nobody ever sat down and is like, okay, let's stop research on this. It's not yielding result. That never happened. A lot of people poured money into it, be it government, be it private entity, be it public entity, meaning money has been continuously being flowing into this field. And from a research point of view, it also makes sense, because if you can truly understand shock waves, shock fronts, and this sort of architecture, basically this chaotic architecture, it will help us to refine other things also. So NASA made the head news like 2 years ago. And then you have Japan, again 1 year ago, I think. US Navy, that has been continuously working. This sort of engine is from US Navy. You have Rocketdyne. Every Tom, Dick and Harry who can work on it is working on it. So there has been serious progress. So what's the dream? The dream is that it's going to give you around 5% extra power. Now you have to understand the fuel content, basically your propellant mix has an energy content that is not going to change. If you had 1 liter of liquid hydrogen, the energy content of that 1 liter of liquid hydrogen is the same in space shuttle era, is same as right now Raptor era, is same. It's never going to change. So the amount of energy is fixed. If we know, and if we can calculate how much energy we are actually getting in terms of moving our mass, you know for a fact that we cannot just magically double it or triple it or go exponentially more, because we have reached that point. So 5% is most realistic approximation at this point in time. Now, what will that 5% allow us to do? Well, all it will allow us to do is either make rocket smaller. So let's say your rocket is huge and you're like, hey, it would be better if you can make it smaller. You can make it smaller. Or you could be in a scenario where it's like, hey, I built a huge ass rocket, let's say SLS or Starship. You can be like, instead of shrinking it down, you can just like, hey, all the structures remains the same as long as you can handle the pressure. Let's just increase the capacity. Instead of 100 tons to low Earth orbit, maybe carry 120 ton to low Earth orbit. That's a big deal. So that's the idea behind it. That's the dream. That's why everybody is pouring money into it. And this puppy would be a perfect fit for arrow spike nozzle. It's not a perfect fit for normal nozzles, because you have to know normal nozzles are awesome. You give them high velocity, basically low velocity, it can make that into high velocity. You can give them high pressure, it can make them into low pressure. It's acting like a transformer, basically taking super high pressure and low velocity and making them into basically high velocity and low pressure. That's why like you have shock diamonds, because the atmosphere is crunching it down. So this is awesome technology, but it does not like shock waves, meaning it's a very stable system. It requires a stable architecture, meaning if the pressure is like constant, like 500 psi, it's like, I got this. But if pressure is like 500 psi, 400 psi, 500 psi, 400 psi, it's not going to last long. Now, when you are talking about shockwaves based system, when you have donut and shockwave is going around from a slice of it, take a slice of it, that slice is going high pressure, low pressure, high pressure, low pressure, high pressure, low pressure, and it could be very, very high frequency, because again, some of the rotating detonation engine, those have like 20 kilohertz, like it's going super duper hyper fast. So that nozzle, it's gonna be fatigued or destroyed instantaneously. So arrow spike nozzle is the only way where you can have that for long term, and not, it also needs to be far more robust in terms of handling the temperature and pressure. So arrow spike nozzle is well suited for it. Can you make it into a nozzle? Yes, but it's not recommended. And what would be the jump? Like how can we quantify it? The jump would be same way SpaceX went from Merlin engine to Raptor engine. That's a big jump. Imagine same jump again to this. That's the desired output. And we have already reached theoretical maximum, meaning what about rocket engines? Like we had signs of it narrowed down as early as V2 rockets, basically World War II era kind of it. And mathematics, we are surprisingly good at mathematics, and I'm like sometimes shocked how far out our mathematics is. Like mathematics that are being done right now, 100 years from now, somebody's gonna like, damn, they figured this out in 2020. So same way in our rocket engine, like again, because money was not an issue during Cold War, they built full flow stage combustion system. Like they built it, and pressures were bonkers. Temperatures were idiotically high. We figured all of those things out. So we kind of know how far we can go. And we are almost at a point where it's like, really do not have that much scope left anymore. Because again, fuel part is fixed. So we cannot extract magically more amount of energy. So all the vectors where we are refining, the refinement is making it more reliable, making it more robust, making it more easily controllable, making it throttleable. That's one thing. Back in the days, we were like, more power. Now we are like, hey, power with control. And making it easy to mass produce. Those are the vectors where every rocket scientist is working right now. Can you expect an engine in the future that will be like exponentially more powerful? No. We reached a point where it's like, that's not going to happen. It's like, will it be a little bit better? Absolutely. But it won't be like, whoa, like going from V2 rocket to modern system. That big jump is not going to happen anymore. Because again, combustion efficiency is almost reaching point. We can do the calculation. It's like we are almost at 90%, almost. So there is only 10% left at best case scenario, and entropy does not allow you to reach 100%. So realistically, you're not going to get too much. Like big jumps are very hard and difficult. So that's the dream of it. So let's come to the paradox aspect of it. Now the paradox aspect is a rocket market, the ecosystem is now an open market. Back in the days, it was a locked ecosystem. Basically, governments were the only ones strong enough, rich enough to invest into it. Be it USA, be it Soviet Union. These were to the big daddies at that point in time. So they were giving open checks. Basically, you want to build RS-25, build it. You want to build RD-180, build it. There was no limits on the cost, so to say. Now we have a lot of limits in the cost. Why? Because we have a lot of competitor, meaning ULA went from like, I got everything to like, oh damn, what do you mean I have to compete in actual financial sense? SpaceX is there, Rocket Lab is there, other companies are also coming in, and Relativity Space is also about to reach complete success. Dragonfly is there. A lot of companies are working their ass off. So in this sort of open market, you have competition. What does that mean? That simply means staying cost competitive is the core advantage, meaning you can have a scenario, hey, I have this liquid hydrogen rocket engine. That's super awesome. If you want to do deep space mission, it can allow you to have extremely high delta V. but people may not use your system. They will like, hey, couldn't we make satellite, the payload lighter, so we can work on much less delta V? We're like, why? Again, rockets are cheaper. So that's how ULA reached a point where like SpaceX was an actual competitor, even though SpaceX rockets tonnage to low, basically deep space mission is not that great. That's the whole point. Remaining cost competitive is the critical advantage here. Like if you are not cost competitive, you're gonna go poof. And delivering high cadence is the key. Meaning, how the heck Rocket Lab became such a successful thing? Like, were their rockets the cheapest per ton wise or per kilogram wise? Hell no. But they had a very unique target. They noticed there is a flaw in the system. The flaw in the system is that if you call up SpaceX for a small satellite, they're like, bro, you have to wait like 6-7 months. And you call this puppy up, they're like, bro, I got this 4 months. And then they were like 3 months. Now they are like, dude, almost 2 months. And they are working their ass off. And current rate of their growth, they may reach a point where there's like 1 month. So that's the whole point. Cadence and cost competitiveness. That's the market game now. It's not like having the latest and greatest technology. No, no, no. It's like, can you make it cost effective? Can you make it quick enough? And what does this mean? This simply means small jumps are not desirable anymore. Meaning, if you're going to say, I'm going to take X amount of money to develop something, this is a bit better, people are not going to give you that X amount of money. So what do we need at this point in time? All the markets are working on what we call quantum leaps, meaning it has to be fundamentally better. So for example, going to 3D printing a rocket, that's fundamentally better to everything else we had. Because instead of rocket being limited to a one design, you are making it into a basically 3D CAD file, so to say. You can change the CAD file, refine it, modify it. You have any failures, you reinforce it on CAD model, and then you just have a print it out. And it can, in principle, can be so fast that all the process can be done in as quick as 15 days, meaning from raw material to full finished rocket in 15 days. That's a quantum leap. Like best case scenario, building a giant factory, then barely having a scenario where you have one rocket engine per day, and let alone, let's not even talk about how long it's going to take to build a rocket. This puppy are like 15 days. Material, printer, output, done, go home. So quantum leaps, everybody is working on. Like again, even this people, electron rocket, successful rocket. They knew for a fact that it's not going to last very long, so they are building neutron rocket. So what is the key of neutron rocket? Smaller than basically Falcon 9, but quicker than Falcon 9, and while increasing the capacity of this. So they are giving you two vectors. It's like, we are not the cheapest, but we are very quick and cost effective compared to every government agency. So that's what we market is seeking at this point in time. Quantum leaps, meaning it has to be exponentially better. So what are the vectors where we can do that? First is 3D printing. That is a quantum leap. Second is in-space refueling. Because here's the deal. If I give you two rockets, they are cheap rocket. You launch one, that is your payload. Then you launch the other one, refuel the first one and go. That is exponentially far more powerful than, oh, my rocket engines are a bit more powerful. Fundamentally, like instead of carrying 100 tons, you are carrying 120 tons. That sounds awesome. But if you have invested in space refueling, because again, this is a complex technology. It's not like, oh, we can just do it. No, no, no. You have to spend millions of dollars to figure this puppy out. So, and again, money is a limited resource. You cannot just like, okay, I'm researching in this and that. No, no, no. You have to only research on one thing. Again, money is limited. So from 100 ton, you will be like, hey, we can only launch 100 ton. We're like, oh, these people is launching 120 ton. You're like, yeah, we can launch 100 ton to Mars. Competition ended. That's what we call by quantum leaps. That's why in-space refueling right now is the most profitable aspect, and 3D printing is the second most profitable aspect. That's the paradox. Is this technology good? Yes. In principle, this technology can truly give you 3 to 5% more boost, but that 3 to 5% is no longer as desirable as it would have been in Cold War or ICBM development. So what we can expect in the future? Well, I have looked through the basically NASA's research paper and US Navy's research paper, and outcome is always the same. It's too many unknown and it's inherently unstable. So what does that mean? That simply means whenever you are building engineering things, there is a rule. We call it rule number 1. Complexity is the enemy of reliability. It does not matter how advanced it is. If you have complexity, it's the enemy of reliability, and you want to make things reliable. Other than that, nothing else matters. You have this amazing thing, but it fails most of the time. Nobody's gonna use it. So inherently, we are working towards making something that is dumb stable. Basically, nothing goes right and is still stable. That's what we want. We do not want to like, okay, this detonation wave is going and it's like very difficult. Like they want to have 2 detonation waves that are going like this, and they randomly end up, hey, wait a minute, why the heck there are third wave? And then the third wave catches up to second wave, it becomes higher speed and boom, the engine goes boom. It has happened. So it's one of those things that on paper it looks so amazing, but stability wise, and they're like, we're gonna develop this technology to compensate it, to fine tune the timings and all that. It's like, We have normal rocket engine that just works at this point in time. So that sort of unknown instability is not desirable. And weight and noise is although other aspects that you have to also take into consideration. For example, there was a craze of pulse detonation engines because again, it's a detonation engine. It has far more pressure. It has far higher velocity. In principle, it could even allow you to build hypersonic planes that are running on normal jet propellants. Jet propellant, why I'm saying JP1, jet propellant one. It could have been done. Like physics is there, chemistry is there. It's just that engineering, even if you can push through the engineering problems, then there is a noise pollution. These things are noisy beyond belief. Meaning, when you're talking about launch pad, imagine your launch pad turning to dust. That's happening with a current system, current Raptor engine. Imagine a rotating detonation system. Your launch pad will become, what launch pad? There was no launch pad here. Like it will annihilate launch pad. Because again, you have shock waves coming out of your engine, not high pressure and high temperature, like shock waves coming out of all engines continuously. So it's very, very noisy, and weight is also higher because rockets are very weight sensitive. These basically aerospike engines are much heavier, and when you're talking about much higher pressure, much higher temperature, inherently you have to work your ass off to make them lighter or use much more complex alloy. For example, in NASA case, they were using distilled water. I did not even realize they had to use distilled water to cool it down. It did not make sense. Then it's like, water has the highest heat capacity. So it's one of those things. Now, are there any places where this technology makes sense? Absolutely. There are two places where they're like, shut up, take my money. Gas power plants. Now, why is that? Gas power plant works continuously, 24/7 sometimes. So if you go to them, it's like, bro, this expensive technology, employ that. It will save you, let's say, 5% per hour. They're like, shut up and take my money. Because again, fuel is expensive. And when you're talking about like 20 years of a plant operation, the fuel prices are constantly going up. So having 5% more efficiency compared to your competitor, that's like, shut up and take my money. That makes sense. And what about the noise? Again, because it's a fixed location, they can isolate it. They can reinforce the sound barriers. You can't do that on a rocket or a jet plane. You can do that on a fixed area plant. Then we come to marine jet engines because today USA have this flagship which we call super carriers. Now super carriers are super duper hyper powerful. Why? Because they have 4 reactors and they only need 2. I did not even knew that, like they were that overbuilt. And somehow there is a top secret button, so to say, that captain can press and all 4 reactors will work at full power and this puppy flies. Meaning there are satellite images. There's this super carrier and they had to deploy, like, go now. People launch onto the satellites are like, oh, okay, that's there. Randomly, it's like Gulf of Moscow, How the heck that happened? Like, how the heck something that big, something that heavy moved that quickly? Again, 4 reactors going bonkers. Now, that created a problem for US Navy, where it's like, super carrier should never be naked. It should never be like, I'm here. It should always have a flotilla, like, for armor within an armor within an armor. And it's just like, lol. That's vulnerable. Now, again, the last time when they did this sort of stupid stunt, they were going against much inferior adversary. But if they were going against warrior class adversary or no equal peer, there was a very serious risk they could have lost their flotilla, so to say. So they need marine jet engines that can be far more fuel efficient because there is a limit how much fuel you can carry. So, and again, there is no weight penalty, so you can actually make it much bigger, much more robust, much more reinforced. So you can handle the sound, you can handle the pressure, and if you increase the efficiency by 3 to 5%, now you can keep up with a nuclear powered system because you can't put nuclear reactor on every small ship. So from their point of view, they are like, shut up and take my money. That's why they are working so hard to get this puppy working. And it has too much complexity for too low yield, meaning it's like, yeah, you invested $500 billion on this technology. How much betterment you got? That's why I said, like, always compare it to other quantum leaps that people are offering. Like in-space refueling is inherently a dumb technology. We have not refined it, but it's inherently a dumb system. It's a liquid in space. It has sloshing issues. It has pressurization requirement. We have this sort of things on Earth also. And we have sorted this out. Like we have mid-air refueling. So it's big, more complex than that, but it can be done. Detonation system, it's a detonation. So low cost construction and mass production, that's the key aspect here. That's where everybody is pouring their money into it. And the people who are not pouring into money in this, either they are government backed or they're going to go poof. There is no other alternative here. And rockets are now commodities. Nobody is even talking about rocket as a big thing. It's like, commodity. They're very price sensitive now. So what does that mean? Price sensitive simply means if you have mild gain and you have exponential cost, it's waste of money. If you have exponential gain for minor cost, it's worth it. And it also happens in computer industry also. It happens in everything basically. So when we can see this sort of technology coming into rockets, when rocket technology will reach a stagnation phase. For example, why did not we had folding technology back in the day? Well, we had it. OLEDs were always flexible. From day one, they were flexible. Like back in like 2010, they were flexible. Why did not we had folding phones? Because market was growing. There was no stagnation there. Once we reach a stagnation point where everything is same, then people do it to, differentiate them. So once we have a scenario where all rocket companies are kind of like they are same kind of cost, same everything, then some company will take risk. It's like, hey, to differentiate, we'll try something different. So you need many years of stagnation before this sort of technology makes sense. Now, what is my prediction here? Basically, unlikely to replace a Raptor engine. Small ones, experimental ones, go YOLO on it. But like in terms of like actual rocket engine replacement, this new technology of engine, anytime soon it's not happening. Best case scenario is 2035 before we see a actual rocket. Like, I'm not talking a sounding rocket or small rocket, Japanese rocket. I'm talking like big daddy rockets. That's why I classified Raptor engine replacement. It's gonna take some serious time. And again, I'm very optimistic with this 2035. So what it's very close to, it's almost like how Concorde was. Like it was a novel technological demonstration. Cost killed Concorde. Same thing could happen with this. And be mindful, whenever you are seeing rocket going like this, you have to understand this is a cost fallacy. Basically, they are pumping money into this technology. They cannot just like, okay, now we redo all this boom again. It's very expensive. So they cannot just like, oh, all the booms we did, we have to redo all the booms again. Very expensive, very painful for your pocketbooks, so to say. So the likelihood of this technology becoming a true replacement very far in the future, and there is a very good chance it could just become a novel tech, unless you are talking about marine jet engines or gas power plants. Those people are like, dude, please develop this technology. Everyone else is like, I don't know. So this was my presentation on rotating detonation engine. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.